On this note page here, we're going to look first at what kind of mirror is this? Can you tell when it's curved this way and the rays of light are going in? This is a concave mirror. Again, I want to reiterate, what's the job of a concave mirror? To pull the what? Pull the light together. Now these rays we don't have to worry about measuring with a protractor. Because they're parts of a circle, you can actually define these with geometric proofs. So we're just going to use them and not worry about proving it or measuring. And they are as follows. Ray number 1 is any ray of light that comes in parallel to the mirror, parallel to the center line called the principal axis, gets reflected through the focal point. So in other words, the job of a concave mirror is to try to grab light and pull it together. And it turns out that if you have rays of light that come from far away, they will reflect right through the focal point, just like so. And how can you find the focal point of a circular mirror? It's real easy. The circle that is defined by the mirror, if you chop it in half, right in the middle is called the center of curvature. And geometrically, you can derive this with proofs there. The focal point is half the center of curvature. So again, let's say I had a circle that was like 100 centimeters around, 100 centimeters, then the focal point would just be what? If I had a center of curvature that was 100 centimeters, for example, my focal point then would just be what? 50 centimeters. So in real life, can you think of an example of when you would ever want to pull light waves together at a single point? Suppose you want to build a solar oven, alternative energy. You set up a giant concave mirror. Actually, Arizona would be perfect. They got these solar farms here. You collect all the sunlight, and right here is where you would put like your hot dog to cook it. Or you put up a big water tower there. You boil the water. It turns into steam. You turn the blades of a turbine. You can generate electrical power for an entire city. Pretty cool, right? Okay, next, ray number 2. Rays of light are reversible. You can almost figure it out. If this is a focal point, instead of a ray coming parallel and then through the focal point, ray number 2 is any ray of light that leaves from the focal point will come out parallel to the mirror, parallel to the center line called the principal axis. If you drive at night, you would want to have a headlight where you put the lamp right at the focal point. If you ever look at your headlights, there's a reflector in there, and the bulb is located right at the focal point so that the rays of light will come out in a nice tight beam. Ray number 3 is a ray of light that hits the center point of the mirror. This is called the vertex. Here's a little trick. If you have a ray of light hitting a curved surface, how can you figure out what happens? You draw on a line that only touches at one point called the what? The tangent line. And then the law of reflection applies. And all that is if a ray comes in at 45 degrees, it's going to leave at a what? At a 45-degree angle, right? If it comes in at a 60-degree angle, it's going to leave at a 60-degree angle, so on and so forth. This one we don't use a lot because it's a pain to draw. You really should like measure it out instead of eyeballing it. Yeah. What I want to point out is these other rays, they still obey the law of reflection, because at each of these points where it hits the curved mirror, we could, if we wanted to, draw on a tangent line where it only touches the curve at one point, and then apply reflectional symmetry. But because it is a principal ray, it obeys optics along parts of a circle. We just use the definition, proved geometrically. Finally, we have ray number 4. This is my favorite one. Ray number 4 I call the lazy man's ray. And all it is if I have the focal point here, any ray of light that goes to the center of curvature will just bounce straight back through itself. But how do you find the center? Real easy. You can take your ruler and measure the distance there on the page there. And I'm going to do it on the paper because on my screen I zoomed in. So it looks like it's about 1.4 centimeters, let's say. So if this is 1.4 centimeters here, the center of curvature is just going to be another what? 1.4 centimeters this way, right? So there's my center of curvature. So any ray of light that goes through the center of curvature hits the mirror, and because it's the center line of that mirror, it just bounces straight back. It's like the diameter going straight back there, right? Through that center of curvature there. So what we're trying to do is we're trying to define 4 rays called the principal rays for mirrors that are derived using geometry, geometric proofs. So on our little practice page, what we're trying to figure out is why when you look in a concave mirror, when you're far away, you see yourself upside down. And here's the basic idea. I'll just show you guys how this works. It's real easy. First thing is we pick any object, we represent it by an arrow. So in real life, you probably never look in a concave mirror other than if you have like a makeup or shaving mirror. This is your shaving mirror in the morning, and you're going to take care of all these crazy whiskers you got there, right? You got your little goatee going there. So anyway, we use an arrow to represent any object. Now, the rule of thumb is how many lines determine a point? You need what? 2. So we just need to pick 2 rays. So the trick is you always locate where the tip of that arrow is. And why do we pick an arrow? Because it's easy to figure out which way it's pointing. That's all. So pick any 2 rays, 1 through 4. Give me one. Ray number 1. Let's see ray number 1. Ray number 1 is simply any ray of light that comes in parallel to the principal axis, parallel to the center line of that mirror, is reflected through the focal point, just like that. It's going to bounce and hit the mirror and go right through the focal point. Put an arrowhead on it and label this ray number 1 so you don't lose track of which way the ray of light's going. Do we know where the image is formed? We don't. We need a second line. So let's pick another ray. How about ray number 2? Why not? And what's cool is it actually doesn't matter which 2 of the 4 you pick, because theoretically, if you draw them correctly, all of them will converge at the same point where the image is formed. So ray number 2 is any ray of light that comes in through the focal point is reflected parallel to the principal axis, like so. That's ray number 2. And here's how you figure out where the image is. Quick question, does your eye see the incoming light or the reflected light? The reflected light. Draw a little eyeball next to the reflected rays there to help you remember that that's what you see. And the rule of thumb is where the 2 cross, X marks the spot. This is where they're crossing. You see that? And notice it is formed above the center line or below the center line. It is what? Below the center line. So that means that's where the tip is formed. The rest of it's right above that. So in real life, if you look into a concave mirror from far away, you will see yourself upside down and smaller if you are far away. I'm trying to draw Eric smaller. I don't know how to do that. So if you have a shaving mirror and you look at inside that concave mirror from far away, you're going to see yourself upside down and smaller. So the technical term for that is, if you're upside down, is it upright or inverted? Which one? Inverted. You can check that off. Is it bigger or smaller? Well, how do you know? You can measure it with your ruler or just look. And in this case, it's obvious it is. Which one? It's smaller. And then, is it real or virtual? The only time you're going to get a real image is when you get an image that is upside down, because a converging mirror and lens is the only thing that will pull light together. When you pull it together, it ends up getting flipped. So on a camera, I don't know if you ever noticed, but if you get too close, you actually can't take a picture. That's because you're inside the focal point, so you actually can't pull the light together onto the film or digital sensor. This is a nice diagram I got out of a textbook. When we light a candle, see how the image is upside down? Why the heck is that? Well, if you look at how the rays of light are pulled together, there's ray number 1, in parallel through the focal point, out parallel. This is actually number 4, what we called it. The light ends up getting pulled together and flipped around. It's as simple as that. In real life, it's useful to be able to pull light together and form an image, telescope, camera, etc.